looking at doing letters of map revision with something other than the traditional HEC2 or HEC-RAS model that has so prevalent throughout the flood insurance program. And as I'm sure you're aware and you're interested in this webinar, there's been a lot of change in the program, even within FEMA itself. They've written in more details and information about two-dimensional hydraulic modeling. And we're seeing that used more and more in municipalities, etc., as they model. So Zach and the support staff have been getting questions, and we've been working with a lot of consultants that are preparing models to submit as letters of map revision that are the one-dimensional, two-dimensional integrated flood models. So we're going to talk about that today. This is again intended to not take the full hour, and to be a little more technical. So we'll have some plain old text slides, but we'll try to talk through some of the details as we go. Just a little bit again, and looking at the fact that the National Flood Insurance Program has, I think, for the most part around the U.S., been converted to digital flood insurance rate maps. Most communities have some version of those, and studies dating 10, 20, 30, some even 40 years old. So there's quite a bit of legacy there, and it's starting to span a variety of different softwares, methodologies, etc. And I want to also mention a lot of times doesn't get any mention, and that's the flood insurance study report itself. That's typically volume 1 of a study, and that describes some of the conditions of the community or the study area, maybe topography or climate. A lot of times there will be different hints in volume 1 of that FIS report about the various peculiarities in that study report. So the Floodway data table is there as well, and that's oftentimes used in the review process and looking at a LoMR. So the FEMA review process, though, we've also found in dealing with various clients is that it's a variety of things happening around the country. The LoMR process in Region 9, for example, is different than maybe a local authority who has been delegated review authority. So we're finding different reviewing agencies, and certainly there's different regional needs. So the upper Midwest and areas maybe that are flat versus areas that are the arid Southwest or tropical like Florida. Just a variety of different conditions, and each of those kind of lend themselves to different sets of questions during the review process. We're also finding different levels of expertise in that detailed model that maybe not everybody's familiar with. The modeling approach that is used sometimes is affected as well. So I want to there's a lot of things to take into consideration. Again, we won't be able to hit everything today, but we'll certainly hopefully try to get questions answered. So traditionally, again, most of the legacy in the NFIP is the HEC2 model, water surface profile models, or the HEC-RAS. Again, those developing water surface profile, kind of the basics, the backbone of the National Flood Insurance Program was to get some special flood hazard area delineated on a map. That was intended to aid in, of course, flood insurance, the sale of flood insurance, and the rate that they charge for flood insurance. A lot of that has evolved over time, but some of those basic building blocks are still the same today. And the floodway concept, again, the floodway is a concept that is defined. It's a policy, if you will, and so we'll touch on that a little bit today, but it has affected and continues to affect things from the technical detail model standpoint. The models were used, the profile was used to generate some base flood elevations. That base flood was the 1% annual chance event in most cases, and again, notwithstanding coastal situations where we have V zones, but some of these were basic elements of what went into the National Flood Insurance Program, the legacy that we have. Floodway data tables and lettered cross-sections, a lot of the review and or criteria and conditions revolve around constraints, say a floodway data table or a top width or a velocity at a lettered cross-section, things that tie back to some of the administrative regulatory part. And all of that, again, was for the purpose of flood insurance rates. That was to set that up. So what are we using the models for is the real question. And quite frankly, it's many times we approach it from a very different standpoint. So in early times, it might have been just to get that map, just to get a flood insurance rate. Nowadays, we likely have more purposes for approaching that model. For example, I'm trying to do good floodplain management. We're trying to do good floodplain management. We find that we have a very complex system. We're no longer looking at just, in every case, maybe just the river runoff, but what else is connected to it, and how are those interconnected, and what are the effects of those? So we have environmental concerns. We have, and that's water quality. We have water quantity. You know, have we increased flooding, or is it exacerbated by some man-made effect or changes in the physical characteristics? So we kind of transition from the somewhat more sterile, if you will, approach looking at just a flood insurance rate to now floodplain management in our urban environment. And from that urban environment, we pick up a flood insurance model, and it's pretty simple. And it probably doesn't capture the kinds of peculiarities, the kinds of complexity, the details that we have in the model. So the flood insurance model might be just a one-dimensional river model in case back in the HEC 2 days, in fact, early days, we would put in river stations as river miles, and kind of given a sense of the granularity with which we looked at those models. We're on a mile-by-mile basis, and nowadays we want to get down to a few hundred feet, and that can be a challenge for us. So picking up that river model, that legacy model, it was a one-dimensional hydraulics. We need to understand a little bit about one-dimensional hydraulics, and there are several assumptions that go into many of those models. I know there's a few communities out there that have unsteady models. There's a few communities that have full dynamic models, and we'll touch on that here, but just kind of looking at the bulk, the preponderance of the legacy data that we have in the program, it's generally 1D hydraulic steady state, has to follow the assumptions that go along with 1D steady state flow. We may have gotten more elaborate, as sort of the bottom of the slide points out, in the things that we imagine the model sees, but realistically it doesn't. It just crunches that down to a rating curve with an n value and calculates based on that. And then there's some assumptions with that go along, and these are the assumptions that we need to be familiar with, and we'll point out why as we go later on in the presentation. But so for example, if we assume flow is approximately one-dimensional, following a flow path, and it follows these assumptions, then we're good to go with a 1D model. However, as we look at that 1D environment, that complex urban drainage environment again, we see that it may not be so much following those nice, neat assumptions. In fact, what we find many times is it's extremely complex and does not follow those 1D assumptions. So many communities, in an effort to manage urban flooding or urban runoff, have tried to use the existing data or information from perhaps an FIS study, couple that with an urban area that may be flooding, and look for mitigation solutions and alternatives. So thus the evolution from our very basic 1D river mile kind of based model into our complex urban situation, where we have pipes in the ground, we have open channels, we have detention ponds, we have wetlands, we have all sorts of features and characteristics that force us to have to recognize that we're no longer following the one-dimensional assumptions. And so we want to update. We want our model to represent the conditions we have today. We want to do good engineering and ensure that proposed flood, mitigation projects or new developments or other things don't have an adverse impact, either at that locale or downstream. And so we want updated flood information. We know that the 1D assumptions don't represent our complex urban conditions. There may be physical features and things that the traditional model just does not do a good job of describing the flood risk for us. So we want to update, and that gets us into the full dynamic model discussion and the typical application of the 1D, 2D floodplain study. So again, we've had several more joins since we've been going. As we get into some details, we just note again there's a question box, so you can type in a question and send that to us. So looking at some numerical models, recently, or for a long time, there have been a lot of one-dimensional unsteady flow models. XP has been on that list for a number of years, and so that's not very new, but just wanted to point that out. Also, more recently, in the last few years, FEMA has recognized this need and has brought more discussion forward about the two-dimensional flow models, and of course XP 2D is on that list with a number of comments on there, and we'll kind of touch on some of those comments as we go. A little bit about XP one-dimensional and two-dimensional modeling. Of course, the one-dimensional modeling has been around for some time and well benchmarked, tested, vetted, if you will. Two-dimensional is a little more new, of course, just in the last few years in terms of being at the forefront of many of these studies and even some flood insurance rate map updates. And it's important to note that the value in this list of models that FEMA has that meet the minimum requirements of the National Flood Insurance Program, one important thing to consider is that we understand, what the models do. And so some of these notes that FEMA has in here are for that very purpose, to indicate that it needs close look and expertise and understanding. One thing we take for granted in looking at this list is the same kinds of caution or overall knowledge base was needed when the very first steady state one-dimensional HEC2 type programs were out and being used. So as the evolution of our knowledge base and expertise progresses, I think this information will need to be learned by our community, our engineering model development community. So XP-SWIM is on that list. So let's talk for a minute about floodplain management, and we're getting to a couple of things I wanted to point out. Talk about floodplain management. Those of you that are floodplain managers know, follow, rules and regulations that stem from the federal flood insurance program, but also from the states, county, from local municipalities, that all touch on or have to do with the floodplain management. Ultimate goal of that is protect life, safety, and people's welfare. And that's achieved, yes, through the policy and through the regulations, but the backbone, the core, sort of center of those factors is the modeling. The modeling describes for us where that risk zone, that special flood hazard area is. The analogy I've used in the past is that we don't have a tornado risk map per se. We sort of know where there are some areas that it happens a lot, but it's tough to produce that map and then manage or prevent people from moving into a certain area. But floodplain management is not that way. Floodplain management, we can model, we can describe with pretty good confidence where floods will occur, the depth, velocity, hazard, etc. And so we can produce these maps with a great deal of confidence and use it subsequently, of course, for managing that natural process that occurs. So the floodplain management folks that are attending can take that to heart, that we're with that goal in mind, trying to achieve the highest level standard as we can in management. And in an effort to provide service to the community, we of course want good floodplain management practices, want to base it on current best available data, want to utilize technology that is currently present. I hear from many communities and local authorities that they have very complex urban problems put in the mix with levees or sumps behind a levee. Include in that new LiDAR data, new orthos, aerial photography that's updated regularly now. And we have so much information at our fingertips, but yet when you look back at a lot of the legacy models that we have in the National Flood Insurance Program, they're 20, 30, 40 years old. And that's unfortunate. And we now have today tools that we can use this better data, better technology, and putting things in perspective to achieve our goal of good floodplain management practices, protecting health, safety, welfare of people and lives. We certainly want to avoid getting lost in a policy argument so much. So there will be some things here when we talk about Floodway and we talk about approaches that I'm not trying to sidestep, but I certainly don't want to be critical, because some of these policy changes take several years to enact. So we'll look at this and how we can fit this into. So let's get to some nitty-gritty here, some details. We have, of course, a couple of clips here from the LoMR MT2 forum, but more importantly, just some details. We're launching on a letter of map revision. The stream has a current effective model. If it doesn't, or it's not been studied, or it's not in the NFIP, then there's nothing to compare to. And perhaps it's easy to add a stream with XP or some other model in the NFIP. However, if there is currently a stream that is in the NFIP, and it has a current effective model that you can get a copy of. I know that can be a challenge at times from the library, getting a copy of the model, but assuming you do have a copy of that current effective model, the first thing is a justification for not using that current effective model. And this is important. The write-up, I believe the MT2 form instructions specifically talk about that narrative that goes into the beginning of this is critical, is important to describe the reasons that a basic steady state 1D model don't facilitate the applications, and a better representation is needed. So that's the first thing, is that narrative, that justification. And I know engineers are typically kind of short on words, but this is a case where you need to fully explain what's going on. And then we'll talk about hydraulics here and look at current effective, the duplicate effective, corrected effective, pre-project and post-project models, because I think that's where a lot of the questions we get asked come from. So again, just a little blip out of the forms. You see here it asks for duplicate effective, corrected effective, existing, and revised. Natural run, that would be the base flood, 1% inner chance. Floodway run is an encroached version of that. And then there's an option for the datum. So we'll talk about each of these in a little bit more detail. So the duplicate effective model is really mimicking or intended to produce similar or the same results as the current effective model. Now, practically speaking, this is a very important step. When we have, say, a HEC2 current effective model, and we want to build a integrated 1D, 2D model, we essentially are mimicking the current effective model in this duplicate effective model. So I won't say it's a dummy effective, although that may come to mind when you begin to put this model together, but it will not be the full gassed version of your proposed model you're building. It's just to mimic, as their instructions indicate. It has to reproduce the FIS profiles to within 1/2 foot. That has been a challenge at times, I understand, because with a full dynamic model you're dealing with a full hydrograph, and so the routing is not the same as perhaps the old concepts of storage routing that were done in HEC1, HEC 1. But the goal here is to mimic, to reproduce, and this is a quote out of the form instructions, to mimic or reproduce the FS profiles. And that's just a starting point. That is just to get a mimicked version into XP Swim. And that could be just a plain 1D model, for example. The next step would be in the corrected effective model. Now at full on in XP Swim, you're actually working with your river model, and you're going to correct any errors in the duplicate effective model. So it's the next iteration of that model. Add cross-sections, maybe detailed topographic information, must not reflect any man-made physical changes, but that detailed topographic information could entail, at this point, adding two-dimensional aspects to the model. So as a recap, we've got a duplicate effective model, or somewhat you might tongue-in-cheek kind of call a dummy effective model. Then we're going to go to our corrected effective model, which is going to bring in some new information. Still limited. This is not the end product, but it's still limited. We're just taking steps now to get to the end product. And then we're going to go to what they call an existing conditions, or a pre-project model. So this is where we modify the model. We can go in and include urbanization, storm drains, all of the peculiarities of things that have evolved over time in the floodplain. And this, of course, this analysis could establish if a more up-to-date model on which we base or do a letter map revision or a physical map revision, and move on from there. If this is for a project, then we may then include the project. Maybe it's a roadway crossing or a bridge. Maybe it's a development of some kind. Whatever the case is, that if we're doing this, then our pre-project model is modified to reflect some post-project conditions and incorporates any physical changes that we've associated with the project. So again, starting out with our duplicate effective model is the key. And your fully dynamic duplicate effective model is the pivot point then to introduce the 1D, 2D integrated model. Now, along the way, there are, obviously, there's a lot of detail in some of these steps. For example, being clear in your narrative about the changes from each of these steps, to step to step to step, adding perhaps the two-dimensional flow. Within XP, there's the ability to have points or lines where we read flow, depth, velocity, total volume, etc. So if there is a bypass, for example, and the HEC1 model, or excuse me, HEC2 model has a note that just says it's, you know, losing flow here, so there'd be a Q card in the HEC2 model that reduces the flow and then comes back in somewhere downstream, and the Q is returned to it. Those kinds of details and things that we can highlight and speak to as to how the duplicate effective model handles it versus how the current effective model handles it. So remember, the duplicate effective is your pivot point, and it's not the final version. The duplicate effective, as we kind of said tongue-in-cheek a little bit, our dummy effective model mimics that FIS profile. It's from there then that we're going to go build on that to produce the different variations of the model. So let's see. Let's talk about, let me back up. There's a few questions, and again, this is different in some of our webinars. I know we have a lot of people on, and we were wanting to be able to have a Q&A a little bit live, but I think we're going to just try to talk through some of these as we go. One of the questions was, pre-project conditions include adjustments to watershed development, influence on hydrology. That's a good question, because some of that is important. So let me talk about hydrology just a second. And if we look at the pre-project model, and we have put in unique elements, detention ponds, for example, cause attenuation, reduce flow downstream. Now, that may invoke a hydrology change that we may have to explain, and it may not change the methodology of the hydrology, but the results of the hydrology. And so that may be the difference. Whereas in the old, in traditional methods, we had HEC1 model or a HEC HMS model that's sort of done in a vacuum, and we take native, what I call native basin hydrology, and you have a Q at the end of a base, a teardrop, say, and it's at a design point. And then you have 5 or 6 other watersheds, and then how does it combine those hydrographs? And then we would do the combine, and then in times past we would do a routing run. So we would go to HEC RAS or HEC2 and then route those, get some storage values out, and put those back into the hydrology model and do quote-unquote storage routing. In a full dynamic model, you don't do that because of the routing is handling the full equation of the shallow water equations, and so attenuation of flow as you go downstream or routing is accounted for in each time step between nodes. So that could very well equate to a hydrology change. Not a hydrology methodology change, but hydrology result change. There's sections on the forums, of course, for that. So that's a good question. I'm glad that was brought up, and that very well could be an effect. The NFIP, and all of the guidelines and specs speak to accounting for urbanization, but we really have never done it, in my opinion, with the traditional models, because they were, a lot of reasons, I think. One, they were separate models. They were somewhat, because it wasn't fully dynamic, it didn't account for the process. But interestingly enough, sometimes the results of the floodplain delineation look very similar, but I think that may not necessarily always help in floodplain management needs. That may be just an irony of the modeling there. But so, okay, let's look at a couple of the questions here before we go talk about floodways, because that's involved discussion. So difference between an effective model and pre-project. So duplicate effective is the effective model run on your hardware or on your machine, I think is how they describe that. So essentially, for an XP swim, going from a steady state 1D model to a full dynamic model, the duplicate effective will be that model mimicked on your machine. So as it says, you'll reproduce the FIS profiles. And so we kind of tongue-in-cheek called that our dummy effective model, but it's our beginning point to then go through and correct it, add terrain, add topo, etc., but no man-made changes, add cross-sections. And then the pre-project is actually, there's another term they use for this is existing conditions. So pre-project might be a misnomer. In your case, if you're just updating a flood study, it could be just, this is the existing conditions model. The effective, duplicate effective is the effective model run on your machine. Then the pre-project model could reflect existing conditions as they are today. Maybe development, ponds, wetlands, diversions, maybe it's been dammed up or something, whatever the variety of things that can be existing conditions. So, and then let's see, there's one more, corrected effective model, the same as a pre-project conditions model, and the corrected effective is not. The corrected effective cannot have any man-made changes. And then the existing conditions would be where you say we have man-made changes. So that's, I believe Ryan asked that question. So, okay, let's talk about floodway. This is a juicy topic here, and everybody is, I'm sure, curious about this one. Of course, floodway is a concept. It's not a real world thing. It's just the idea that if everybody encroached on one side or the other of a stream for the length of it, it would have some cumulative effect if magically it all did happen, and it would look like what is shown on the FERM flood map as the crosshatched area. It is a policy element written into the 44 CFR rules on the National Flood Insurance regulations of the National Flood Insurance Program. It is a 1D concept as it stands today in in the U.S. as a National Flood Insurance Program, meaning that it's based on the concept that you have cross section, some distance, and another cross section, and then you can encroach it. And XP has for a number of years had all these you see here on the slide, all these encroachment methods. I believe the same as most other encroachment approach methods that have been taken. So there are a couple of rules, I guess, with the floodway. Encroachments can't go beyond the left or right top of bank, and you try to minimize it, in most cases less than a foot of rise, and that is built in an automated fashion in XP Swim and can be done. Now, some have said, well, what if we have a two-dimensional model then that's associated with that's out in the overbank meadow area, the flood fringe area, and all of that's two-dimensional? And there is not currently, or if the entire river is modeled with overbanks and all, is a two-dimensional model. There is not a two-dimensional encroachment method because you're at an element. You're not looking at a cross-section. You're looking at an element, so the concept does not carry over. There have been a couple of proposals suggested for ways to do floodway if you have an integrated 1D, 2D model. There's some ideas. I believe Australia has a methodology that they use if it's all a two-dimensional model, and you look at kind of velocity classifications, which kind of lines up with our concept of the floodway, which is where the preponderance of the flow and velocity is. So, but currently there is not, and it always gets to be a tricky discussion. One community that I'm familiar with has elected to make the floodplain the floodway, so essentially no encroachment. One community has said our floodway is equivalent to a 25-year floodplain, so they run a 25-year event, and that delineation of that becomes the floodway, and it has the same floodway concepts. Interestingly enough, matches pretty well with a little wider, the floodway concept, but have encroachments. So a little bit about that, just to mention. So again, this kind of shows that on the right side here, the 1D, 2D integrated model, typically where that cross-section is prescribed and the one-dimensional flow within there is still a good method and assumption, and I believe that's the case. And at times, then we attach or indicate outside of that area we have two-dimensional flow. Once it gets out in the flow or the overbanks, of course, then it follows the terrain and the two-dimensional solution, two-dimensional hydraulic solution. So there's not a floodway for that area, and not able to do it. Okay, let's see. That was it on the floodway, and yes. So there was a question about equal conveyance reduction on both sides. So go back to that slide, and we have equal right and left conveyance reductions, and that's in the 1D now. The 1D. So the floodway for the one-dimensional model does manage that equal conveyance loss at because the 1D model is just cross-section to cross-section, so it's the same concept of encroaching on that. Okay, a little bit on, and there's some good questions coming in. We'll get to the, I want to go through another section here before our time slips away. Check models. XP has built in several model checks, right? This is somewhat new, and it's not a black box. We need to know what we're doing and what we're using and how it's working. So XP has two-dimensional simulation summary, and I'll show you that in just a second. But there's another couple of tabs here I want to point out. Show errors. That can be very important when reviewing the quality of your 1D, 2D model. And we call those integrity errors as well as two-dimensional errors. And the model won't run, by the way, so you can know heads up in advance what the problem is. We have another thing called output logs, and this is where you go in and can see details of the output itself. And warnings. This is much like warnings in HEC RAS. You can see the warnings. Well, here we have these logs you can pull up and see perhaps the same kinds of warnings and or conditions. The 2D summary is sort of a heads up, of course, because it's enormous amounts of data. It's really best viewed graphed. And a lot of people worry that, in two-dimensional modeling you could change some setting somewhere and fake it, to be a good model. But the idea here is we've put this summary in a screen so you can see this is just showing change in volume. So you would be worried if your model grew or lost water. And so some startup to balance is normal. You can see the curve goes up and then it goes down. But then as it progresses on, and this is not showing the entire simulation, say it's a 24-hour simulation time or a 30-hour simulation time storm event, you would expect that to get closer and closer to zero, balancing the volume as you go through the entire simulation. So that graph shows you that. In the top part here of the screen, it shows wet-dry depth and coefficients and runtime and things like that. All of those are signs. If somebody played with parameters. Right here, you can get, and this window scrolls down so you can see there's only about, I guess, a half dozen more parameters, and that's it. You can absolutely review the input parameters from this window, and that makes it good for review of information. So a couple things to point out. One thing that is a predominant factor in two-dimensional flow analysis is the N value, as most of us know, and so a lot of times we want to, in XP, we bring that in through what we call a Landuse. It's saved in a global database so you can reuse them. Then you can visualize them by turning them on. So we brought in roads, pastures, some buildings, some vegetated creek, etc. And we import those right from GIS. We could draw them heads up in the software, but in the user interface will allow you to do that. But we already had them in GIS. We brought them right in. Know the quality of that GIS before you bring it in. It may not be exactly what you think it is. So some of them come in with just millions and millions of little vertices, and that'll really slow down your model. Well, that's not necessary on an example like these roads. But at the same time, you want to verify the quality of these GIS files that we're bringing in, because that's going to affect the roughness, which of course majorly affects the results in the 2D model. And so I just want to point that out as we're looking at this, and we're wrapping up. We're getting close on time here, so I'll hurry up. Terrain data is another big issue, because now we started out 10 years ago, everybody was starving for some LiDAR data, and now all of a sudden, today we have bombardment with horrendously large, enormous sets of data. So we kind of swung the pendulum there doesn't necessarily make it a better model just because we have a billion points in our surface. And to illustrate that, I want to show a slide here. This was put together by Jeff Wenger and Brown and Gay. And so at the very bottom of this, you might see that nav. That's what you and I would see if we looked down the site with our binoculars. But by the time you progress up this, these steps, you know, you go through from the LiDAR data, and then we start looking at ultimately the very top. When you have a two-dimensional model, whether your model is a mesh with a triangle, or it's, in XP's case, a grid cell, that's all it sees is that cell. Right now, currently on the market, what they're looking at is that cell, and the depth is averaged for that cell. And all the softwares, to my knowledge, are the same, and look at that for calculation purposes as a cell. So let's not romanticize or over-imagine what our two-dimensional model sees. It sees this terrain as a cell. So more is not necessarily better, but certainly we want our good terrain, and we want it to pick up all the undulations that we want our model to see. So XP focuses on what do we need to do to build a good model. We're not trying to be terrain modelers per se. So there's some tools in there that allow valleys and ridges and things like that. But on using the 2D surface, for, you know, somebody says, oh, we've got great 2D, you know, we've got great terrain data, we'll just do a 2D model of everything. It might not pick up the natural channel. So the resolution could be too coarse. You know, you have to make sure that you're doing a litmus test here. Are we really picking up what we think we're picking up in the model? So I got a lot of questions I want to get to, so I'll just in summary, again, the duplicate effective model is a pivot point, and it's again kind of tongue-in-cheek a little bit here, our dummy model, but we're going to begin from that point, and because we've used that duplicate effective model to mimic the FS profile. And then from that, we're going to build our full-on, ultimately have our full-on 1D, 2D model. Review the output, error log files, make sure you're paying attention to the GIS files that you import, and then the terrain is not necessarily what you think. So a couple of the questions that have come up, I want to answer or speak to. There was a question about some aspects in order to get the hydraulic model approved by FEMA during the LoMR process in a Zone A area. Zone A has typically, as my understanding, has no model. So I think Dewberry, in fact, Sam Crampton at Dewberry has done a presentation for us on where they did a lot of this in areas where you could cover the Zone A very quickly and cost effectively and thoroughly with a 2D model, because what ended up going to FEMA was the delineation for a Zone A, right, because it's just approximate, and maybe the depth if it was needed, but not necessarily a model. So and another question is looking at new HEC-RAS 2D capabilities and how they compare to XP. Bill Syme, the author of 2Flow, has looked at that. I think he's even worked with HEC some on some things, and I think there are some differences in application. This is a great topic and a great question. I think the differences are more in line with your application and why you're approaching it from that perspective. And so I'm sure once HEC-RAS is out on the market being used, I'm not sure, I guess it'll be pretty well documented since there's no support, but haven't seen a whole lot. I guess we'll see what their uses of it are and let the market determine that. Another one is if the topography has been changed due to land leveling, etc. That's a man-made change, and I would say that would fall into your existing conditions model. What's the difference? Bridge replacements change floodplain. Yes. And again, I think you're doing existing conditions when you introduce bridge replacements, and unfortunately I've seen a lot of variety among how communities look at their transportation crossing projects, even though it might affect the floodway and technically has some implications on doing a LoMR being required if it affects the floodway. So I've seen differences there between what the regs say and what people actually do with putting in bridges. But if it's a man-made change, not an effective model, then it would go into your existing conditions. The duplicate effective, going from 1D steady RAS to a dynamic XP. Some of the major hurdles were the hydrology someone touched on. The common issues, I think, had to do with the engineer doing a good documentation narrative explanation process for why the effective model was not appropriate to continue to use, and document that. And then basically, unfortunately, when you change models, you're always on your heels a little bit in defense mode, right? And you just have to explain each and every nuance. I know some people that have started in that path and given up because the explanation required more effort than they were worth. I know some people who have done their designs based on the XP 1D 2D model, but have actually submitted the steady state RAS model, made the RAS model mimic the XP model. So some people have turned it around just to avoid the regulatory, which is, I think, unfortunate, but has been the case in the past. 2D floodways, somebody asked about that again. There's no such thing. Hopefully, at some point, they'll come around to some ideas on that. Again, I think the time to switch from a RAS to an XP model is with the duplicate effective model. Is just right out of the bag. Just get your duplicate effective model and make it an XP swim model that mimics the existing profile and go from there. I think that's the starting point. Please clarify when the duplicate or corrected the 2D model should be introduced. 2D model could be introduced, I think, at the corrected effective model point. If it's man-made changes, I would hold off until you get to existing conditions, the reasons, but I think at either one of those points you could introduce the 2D model. And can you use multiple grids with different cell sizes in one model? Yes, we can. We have finer in the channel or in an urban area and a more coarser grid out in a rural area, etc. Yes, we can. Is there a technical manual for 2D modeling? Yes, there is. And BFE's profiles, another loader name, easy to generate. Yes, the BFEs are a little funny in a 2D model, right, because you have cells. But as far as being able to do it in the software, yes, we do. And the profiles, one of the things about the profiles is you might have to profile additional flow paths. If there's major overflow flow paths, those might become a new subset of a stream in the NFIP, so those might have to have a profile of their own. And we generate that profile in XP. The other LoMR data requirements are in like 1D output or two-dimensional output files. That's a good question. Is there a limitation on the number of nodes that we can use on the XP 2D model? Practically speaking, there is. Technically, no. You can buy unlimited, but practically speaking, you can probably only run, a computer will only run, so how much ever memory it's got. So there are some practical limits to that. I think our time is gone. Thanks everybody for staying in there. There's still a lot of people on the webinar, and we'll keep going here answering questions. We have recorded this, so it'll be up on the website after we get time to reformat it and get it up on the website. So it will be put up on the website. And on behalf of Zach and staff there and myself and XP Solutions, thank you for attending and all your great questions. Again, my email's here. The questions we're answering will be out and available as well as the recording. So thanks everyone for attending, and I hope you have a great rest of your week.